Okay, so let's see. All right, so chapter 7, we talk about normal distributions, where we can pretty much try to convert everything back to normal distribution, and because it's so convenient, it's easy to use. That only one command, normal CDF, depends on which area you want to find, and then you just selecting the lower bound, the upper bound, and then you put 0 and 1 and done, right? So that will give you the probabilities right away as the area under the graph. So everything's gonna try to go back to normal distributions. Now, chapter 8, we try to, the idea is that, okay, so now I'm being good at collecting data already. So now I want to make a prediction for the populations, all right? Because it will be super hard for us to do a survey for the entire US population if we do want to do some research. So therefore, it's always better that we do with a sample to the point where it's large enough to get the most accurate result, and then we can make that prediction to the population. So that would be chapter 9 stuff. So chapter 8, we kind of get ready to make that predictions. All right. So chapter 8 focus on two things. It's focus on the sample mean and the sample proportions. Right. So we'll talk about that in a bit. 8.1 is the distributions of many means. So what it means is that, all right, I'm gonna ask 20 people in the class today, right? I'm gonna ask 10 people in the class today to find out how they feel about the class so far, right? Or stat in general. And I find the mean, so that's the mean of the first 10 people. And then, next semester, if I teach that again, I will ask another 10 people to see how they feel about the stat class in general. So that's another 10. And then if I teach another class of stat next semester, then I just ask them another 10 people to see how they feel about stat in general. And I calculate their means and stuff. So you can see that each time I collect a sample of 10, a sample of 10, and so on. So now I want, suppose that I collect 10 consecutive sample of 10. Now I have 100 people. All right, if I collect another 10, then I continue doing that. So 8.1 focus on the distributions of many means. So you don't go out there and collect 100 people right away, but you do it one at a time in the increment of 10, right? Today is 10, tomorrow is 10, another day is 10. And then you put all that together. And we call that the sample mean X bar, right? The mean of the means, right? So that's the idea of 8.1 focus on. So because of that, we will have means of the means and also the standard deviation of the mean distributions. Okay, so it is the probabilities of all possible values of the random variable x bar computed from a sample size n from a population mean and a population standard deviation x bar sigma, meaning that we will know the population mean and we will know the population standard deviation already. And based on that observation, we will collect many mean to see whether the prediction is accurate or not. Okay. So the means of the means will be the same as the population means. right? So that's how they define that for section 8.1. And the standard deviation of the sample mean will equal to the population standard deviation divided by square root of n, right? And that's what we call the standard error of the mean. So you want to find out that what is the uncertainty of the sum of the mean or the mean of all mean that you're going to put together. Okay, so that's the idea of 8.1. Now, how do we recognize 8.1 compared to chapter 7? 8.1 will only focus on the distribution of the mean. So when you read a problem, you will see they ask you to find the probability of the mean, right? The word mean have to be involved in the question itself, right? In the probability question. Therefore, that's how we will distinguish the difference in chapter 7 and chapter 8. So I'm gonna bring back chapter 7 in a little bit and then show you a big difference between chapter 7 and chapter 8. All right. And I said before, because normal distribution is so convenient, therefore we can try to convert every distribution back to the normal distribution so that we can just use one simple command. So in order to do that, we need to find the z-scores, and the z-score for 8.1 will equal to x bar minus mu divided by sigma x bar. Okay, so if you go back to chapter 7, how we define the standard deviation, right? Z. So z will equal to a random x minus the mean divided by the standard deviation, right? So that's a general formula. So when we look at chapter 8 in comparison, so we also taking a random, but a random sample mean, right? Because 8.1 is all focused on about the sample mean. So we have to take a random sample mean minus the population mean and divide by the standard deviation of that sample mean, right? So we do sigma x bar, where sigma x bar is equal to the original sigma divided by radical n. So all of that information will be provided, right? So they're not gonna let you go out there and find all of that by yourself. So everything will be provided in the question itself, okay? So that's how we convert to z, right? You can look at chapter 7. We take x minus mu over sigma, right? So that's the general formula. Then chapter 8, same thing. X bar instead of x because we focus on the mean, right? Now, you can use this formula, right? You can use this formula. That's totally fine. However, there's a modification of that formula where we can just go directly and use it without doing the second step, right? Right? So we consider this, right? Sigma x bar is equal to sigma divided by radical n. So I'm gonna explain this to you right now, right? So z is equal to x bar minus mu over sigma x bar. This equal to x bar minus mu divided by sigma divided by radical n, right? Because sigma x bar is equal to sigma divided by radical n. So when we divide our fractions, we multiply the reciprocal. So this equivalent to x bar minus mu times with radical n over sigma. And that is what you see over here. So what's the difference? If you use the first formula, you have to find sigma x bar. If you use the second formula, there's no need to find sigma x bar. You just plug in whatever they give you, and then you out of your way with that problem. Okay, so either one, right? So if they give you sigma x bar, you use the first formula. If they don't give you sigma x bar, then you can use the second formula, or you can just have to find sigma x bar by yourself. Okay, so sigma and sigma x bar, they are different from each other, right? Sigma is from the population standard deviation. Sigma x bar is the standard error of the mean, right? Totally different objects. So just keep that in mind, okay? All right, so here we go. Example 1, right? So I'm going to erase this, right? So now I'm going to already explain that to you, where that formula came from, right? All right, the weight of penny minted after 1982 are approximately normal distributed with the mean of 2.46 gram, right? So there we go, right? So that's the populations right there, right? Right, with the mean of 2.46 grams. So that will be meal. And the standard deviation of 0.02 grams. And that guy will be our original sigma, right? Because we know that all pennies minted after 1982 are approximately normal with that information. Now, I just randomly want to see whether it's true or not, right? And I want to find out based on that information. Suppose that I randomly selecting 10 penny after 1982. And I want to compare my means with the one that provided. And I'm asking myself, suppose that I select 10 penny minted after 1982, what will be the probability that the sample mean that I just selected at least 2.465 grams? So I want to see, okay, now I'm going to randomly collect 10 penny and find the mean of that. And what is my chance of the mean that I just found will be at least 2.465, right? So a bit higher than the original mean that's provided. So there you go. We obtain a sample mean of at least 2.465. So that will always in there. If you go back to chapter 7, all right, and then we look at the first problem, right? You can see here that, all right, it is normally distributed with the mean of 100 and standard deviation of 15. So the information is not different, right? So the information is not much different, right? So they give you the mean and also the standard deviation, okay? Okay, so there you go. They give you the mean and the standard deviation, right? Chapter 7, the same thing. They give you the mean and standard deviation. However, in the question itself that, okay, I want to find the probability for an individual who IQ score is 120. So they just focus on the IQ in comparison to chapter A. They want to find the probability of a sample mean, right? So that's how you distinguish the difference between chapter A, point 1, and chapter 7. So chapter 7 will not mention anything about probability of the mean. Chapter 8, section 8.1 will ask you about the probability of the mean. Make sense here? That's how you recognize that, okay, I know it's not going to be chapter 7, it has to be chapter 8. And that's when you start using the right formula for the right place, okay? Because both chapter 7 and chapter 8, we always try to convert to z-score. And because they are talking about different concept, we have to use a different formula to convert to z-score as request, okay? So that's the idea that we going to play around in chapter 8 in comparison to chapter 7. All right, so I want the probability of sample mean bigger than or equal to 2.465. So this equivalent to probability of X bar, right, bigger than or equal to 2.465. All right, so we know a sample of size 10, so n is equal to 10. So you can see here, they give us a sample of size 10, they give us the original standard deviation, they give us the original mean, so it will be better if we use the second formula, right? So I'm going to use the second formula instead of the first one, but I'm going to show you both, right? All right, so this one is equal to probability of z bigger than or equal to 2.465 minus 2.46 times with radical 10 and divided by 0.02. All right, second formula. And then just put in the calculator, and then you should find out what's the z-score for that. So 2.465 minus 2.46 times radical 10 and divide by 0.02. All right, so I have probability of z is bigger than or equal to 0.79. And that's where we normal CDF. All right, here's the questions. Is that the left area that we want, or is that the right area that we wanted?
Right, because it's at least.
That's right. Thank you, Walter. Yeah. Okay. So because it's right area, so we have to start from 0.79 all the way to 10 to the power 99 and then 0, 1. Okay, it's very important. All right, and then you put in 0.79 first, and then 10 to the 99, and then 0, 1, and then press enter. So we get about 0.215. So the chance of the, if I select 10 pennies and I find the mean of that, the chance of that mean is at least 2.465 gram is about 21.5%. So we have about 21.5% chance of the sample mean more than at least 2.465. Okay, so that's the second formula. If you want to use the first formula, can you still do it? Right? Yes, you can. Right? First formula. All right, you need sigma x bar, which is sigma divided by radical n. So you take 0.02 divided by radical 10. So it gives you 0.0063. Okay. So the probability of x bar bigger than 2.465 now can be calculated as probability z bigger than x bar minus mu over sigma x bar, which given us z is bigger than 2.465 minus 2.46 divided by 0.0063. Right, we're still getting probability of z bigger than 0.79. Okay, and then you do normal CDF. Does that make sense here, guys?
Yeah, which method do you prefer? I know
What is
there's two
that?
options. Which one do you prefer?
I probably prefer the second options. You know, if they don't give me the the standard deviation x bar, right? Yeah, because when they give you the mean and then the population standard deviation and then the sample size, all you have to do is just plug it in and then get it in one shot. Versus the other one, you're gonna find sigma x bar first and then use that result and plug it in one more time. So you do two calculations instead of one. Yes, Aaron.
What does that say? The normal
CDF.
Okay.
Yeah. And then sometimes student misunderstood that, okay, it doesn't matter the first or the second, they are using the same sigma. So they use the first one, they just plug in sigma, right? So normally I use the second one so that, you do have to include the sample size involved also. Therefore, the second one would be a much better option for a student to see it more easier compared to the first one. Because, the first one, you have to find sigma x bar no matter what, right? And most of the time, students forgot to find sigma x bar. So I usually do everything with the second formula method for your information.
Perfect.
No worry. All right. So example one is when the populations are normally distributed. And then the second information here is that what happens if we don't have a normal population, meaning that the population is non-normal. Well, there's always a way for this to work. And again, we are just taking this information for granted. But believe me, the statistician in the past, they did a lot of study and research to come up with the theorem that we're going to use here, right? So they call that central limit theorem. So it said that the sampling distribution of x bar become approximately normal as the sample size and increase. Therefore, we will have the same mean and the same standard deviation as in case one, even when we don't have a normal distributed. But if you take more and more, you will build up a better result. It is. And in the end, it will give you a bell curve no matter what, right? So that's the idea. Remember, in chapter 5, we talk about, if you flipping a coin for the first time, you might get head. You're flipping a coin for the second time, you might get a head. So you get 100% successful so far. However, if you do for 1,000 times, the chance of after you do 1,000 times and you record it, the chance of you getting a head and the tail will be around 500. That's what they meant by the central limit theorem, right? So when you do more and more and more, you kind of give every possibility in there the same chance to happen. That's what it means, right? So central limit theorem, as we have a big size of a sample, then we would not have to worry whether it's normal distributed or it's not normal distributed. That's the idea for that central limit theorem. Okay. So and when they talk about the sample means here, they might wonder, all right, how many are considered large enough? So I read from the book, and the author mentioned about if anything that's more than 30, that should be considered large enough for us to be normal distributions. Okay. So a few textbooks talk about that. That's what the normal sample size that for them to consider it is to be normal distributed. Okay. All right. So example 2. Suppose that the mean time for an oil change at a 10 minutes oil change is about 11.4 minutes. So meaning that when you go to a store, you get your car oil change on average is around take them around 11.4 minutes. All right. So that's something that we can use. And the standard deviation about 3.2 minutes. So you can see in example 1 or example 2, those information are always provided, right? So mu equal 11.4 and sigma equal to 3.2, right? So they always give us that option. So you don't have to find it, right? So you find it, then you did something wrong. All right. So they have to give you that. Now, a random sample of 35 oil change is selected. What is the probability that the mean oil change is less than minutes, right? So you can see here what is the probability that the mean oil change is less than 11 minutes, right? If you look at example 1, what is the probability that the sample mean of at least 2.645 in comparison to chapter 7? They just talk about the IQ score, never mention about the mean of the IQ score, okay? So they'll ask that question. So that's how we know the difference between 7 and 8 one more time, right? So I want to find out the probability that the mean is less than 11 minutes. So this equivalent to probability of X bar is less than 11 minutes, okay? All right, so go ahead and finish the rest of that if you can and see what you get for the answer. All right, has anyone got an answer? Matthew got negative 5497. Any confirmation on that? Matthew, probability cannot be negative, so we have to mess up somewhere along the way. Easy, right? Get rid of negative. All right, Julia got pawn 2-3, and Shalin got pawn 2-3. So you got outrun here, Matthew, right? What you got for your z-score, Matthew?
0.125.
Yeah, and because you have to take 11 minus 11.4, so that should be a negative number.
No,
not
negative 0.125.
You times radical 35 and divide by 3.2.
No, I'm just gonna wait for you to do it here and just copy it down because I mess up all over the place.
11 minus 11.4 times radical 35 and divide by 3.2. That's what you have to set up, Matthew.
I didn't do that radical with the. Okay, that's the sample number.
That's right. Yes. All right. Thank you, Julia. Thank you, Charlene. That's the correct answer. You forgot to take the radical, Matthew.
Yeah.
All right. Sounds good here, everyone. So you can see here how amazing normal distribution is, right? If you look at number one, right? Number one talk about at least, mean that it's bigger than or equal. We use still the same command, normal CDF. In example two, they said strictly less than, we're still using normal CDF, right? So we don't need to move one left or one right, right? So that's the best thing about normal CDF. As long as you get your Z-scores, you are good to go. That's why it's so convenient, and we try to make it back to normal distributions.
I actually did it wrong, but I got the same answer. I did 11.4 minus 11, so I did it backwards. And then I did the positive 10 to the 99th. And then I think that's
for that, you kind of flip the situation around. You're looking at, to the right-hand side. It should be to the left-hand side.
Oh, okay.
Okay. Because you did that, because you did that, that's why you got the same answer. Because you flip the two infinity around. That's why.
Yeah, I did. Okay.
Yeah. So always x minus mu, not mu minus x. And if you now make a sketch, and that's how you see it's more clear, right? So this is negative 0.74 for the z, and you want the left area, so you cannot go to positive infinities. So you have to go from negative infinity to negative 0.74. So you can, right? So we'll always travel from left to right, not right to left. Does that make sense, Julia?
Yes.
Mm-hmm. Okay, make the sketch will be the best situation, best advice for you to see, okay, which one I'm gonna put down first, negative infinities or positive infinities, right? All right, so that's 8.1, right? So 8.1 only focus on about the mean, right? And nothing less. All right, now 8.2. So in 8.2, we focus on not just the mean, but what is called the proportions. All right, so sample proportions, right? So what is proportion? Proportion is probabilities percentage, right? So we look for a percentage. So this one here are talking about the number of successful in a sample, meaning that this kind of more lean forward binomial distribution, but they don't look for the value, they only look for the successful. So let's say I want to have 50 multiple choice questions. How many times I'm gonna get 35 questions correctly? So I'm looking in that scenario, right? So they only look for the probability of successful, and they call that the sample proportions, right? Now, sample proportions will always deal with, percentage or, some probabilities and so on, right? Anything involve percentage will be considered as proportion. So sample proportion, we will use p hat to make that notation, right? P hat will stand for the sample proportion. Now, each sample proportion will equal to x divided by n, where x is the number of success in the sample, right? So if I do 50 multiple choice questions and I have 35 questions correct, then that's my number of successful will be 35 divided by 50, right? So that's how we calculate the percentage of number of successful in n trials. That's the deal. All right. Oh, give me 1 second. Somebody knocked the door. All right, be right back. Okay. All right, sorry guys. All right, somebody will knock on the door, do a survey. So I'm teaching a stat right now, so can I handle that? All right. So now in recognizing 8.1 and 8.2, 8.1, you're gonna look for the keyword. I want to find the probability of the means. In 8.2, you want to find the probability of the proportion, right? So now, first thing we need to do is the shape of the sampling distribution of p hat is approximately normal when n times p, and then 1 minus p will be more than or equal to 10, and n is less than 5% of the population. Now, we going to look at two things, right? Don't get mixed up between p and p hat, right? So p hat can only be found from x divided by n, and p will be provided, okay? So p will be provided. So this one here will all gonna be given. So now we need to have the mean and the standard deviation, because in order to convert to z-score, we need the mean and the standard deviation. For the proportion distribution, there is no difference. All right, so now the mean will be the same as the population's proportion. So mu's of p hat will equal to p. And the standard deviations of p hat will be found by using the formula P times 1 minus P divided by N, and everything's underneath the radical. Okay, so when you write your notes for the next exam, make sure you write out the meaning of each of those letters, right? So you know what to plug in for which situation, okay?
I have a question about that. So on the test, if we end up actually using that radical, but not writing it during the equation, you mark us off for that, correct?
For which one?
So let's just say instead of writing the radical of P in parentheses 1 minus P over X, L over N, and I don't write that radical, would you mark me off for that on the test?
Oh yeah, without the radical, it's no longer standard deviations.
But even if I do it in the final calculations, I add it in?
Yeah, that's how you show your work, right? So from the start to beginning, you're gonna show exactly how it's got done. Sounds good, Matthew?
Yep.
All right, so now, as I mentioned that we would try to convert everything to z-score, so it's a convenience for us. So there will be two formula again, depending on which one you want to find, then you can go ahead and use that, right? So z-score, the original z-score value will be x minus the mean divided by sigma. Now, the x is just your p hat, and the mean will be your p, right? Because that's the original mean for the populations. And then sigma p hat is what you need to find. So you can do that, or you can use one formula where you don't have to find sigma x p hat or anything. That would be the second formula. So z equal to p hat minus p divided by square root of p1 minus p over n. So normally I use the second formula so that I can just plug it in everything instead of I have to do step 1 before I can do step 2, right? So the second formula saves us a lot of work for doing that, right? Just like the section 8.1, right? So same thing with 8.2. I'm just gonna go ahead and do that. All right, so here is the example corresponding to proportion, right? You can see the difference. According to the Center of Disease Control and Prevention, 18.8% of school-age children aged from 6 to 11 was overweight in 2004, right? So you can see here, this guy talk about the percentage, so that will be the population proportion. So my little p will be 18.8%, which is 0.188.
Going back a bit, I'm having a hard time understanding the mean mu p hat equals p. Could you repeat the difference between p hat and p?
All right, so p will be the proportion for the entire population, right? So let's say when you read an article, right, say, okay, last year there's about 35% of students graduate from community college, right? So that's talk about the entire population. So that would be our p hat, our p, right? And then you said, well, I don't know whether it's going to be true or not. I'm going to do that research by myself. And then you select a random of 1,000 students and ask you, did you graduate from community college yet? And now you have the number of people successfully graduate from college out of that 1,000 list. And that would be your p hat, right, Grayson?
Okay, so p hat is essentially for a sample, whereas p is for a population.
That's right, yes.
Got it.
All right, so that's why when you see here, Grayson, according to the Center for Disease Control and Prevention, 18.8%. So they renew that. So that will be for the whole population, yeah? All right, now, so that might p, right? In a random sample of 90, right? So now you do your own research, right? So this one here, talk about n equal to 90. What is the probability that at least 19% are overweight? Okay, so now they give you the sample size and they want to find out that what is the probability that at least 19% are overweight, right? So now talk about probability at least 19%. So here in this sample of 90, you want to find out at least 19%. And again, so in this case, we are lucky that p hat is also provided. So p hat will be bigger than or equal to 19%. So you want to find out what will be the chance of at least 19% are overweight, all right? So part A is not at much work compared to part B because part A is already given, right? So we want to find out what is the probability that p hat is bigger than or equal to 19% of 0.19. And then we need to convert to z. So we convert to z. So probability of z bigger than or equal to p hat minus p divided by p1 minus p over n. Then we can plug in whatever the number that we have. All right, so here we go. Z is bigger than or equal to 0.19 minus 0.188 divided by square root of 0.188, 1 minus 0.188 over 90, right? Because that's what we want. So yeah, just be careful here because there's a lot of numbers. So just play around, play safe. I'm gonna do, the top one and the bottom ones, and then we put those things together. All right, so I got 0.002 divided by
Hey, Professor,
0.04. Yes, Victor.
is it okay you share your screen on how you just plug in the numbers on the calculator?
Yeah, for sure.
Right, thank you.
Yeah, so when I'm not, don't want to mess around with the formulas, I'm just gonna do slowly, right? 0.19 minus 0.188, right? So that's give me some answer, which is my numerator. And denominator, I can just do second x squared here. That's where you get access to the square root. And then you put parenthesis 0.188, and then time with 1 minus 0.188. Close that parenthesis, and now divide by 90. Everything's still underneath the radical, and move that out of the way and press enter. And that's how you got the denominator, Victor.
Thank you.
No worry. Okay, and then just do one more division. So 0.002 divided by 0.0412, right? All right, so now I'm getting probability of z bigger than 0.05. All right, so here's the bell shape again, right? So we want to find z is bigger than 0.05. So we're looking at the area to the right. So we go from 0.05 to infinity, right? So you know the exact command you want to put it into your calculator to get the answer, okay? So the probability that p hat bigger than 0.19 is equal to normal CDF 0.05, 10 to the 99, 0, and 1. All right, so we got 0.48. Okay, and then part B, suppose we have a sample of 90 again, and what is the probability that 24 are less overweight student, right? So it's no longer percentage. So this one here, it is X. And because of that, we have to use the formula to find p hat, right? So for part B, n equal to 90 and x is equal to 24. Therefore, p hat will be x over n, which is 24 divided by 90. So we get 0.2667, right? So the probability that x less than or equal to 24 is equivalent to the probability of p hat less than or equal to 0.2667. And then you can convert to z. So probability of z less than or equal to 0.2667 minus 0.188 and divide by square root of 0.188, 1 minus 0.188 over 90. So same approach, it's just different way to find p hat, right? If p hat is given, that we are lucky. If not, we can always find it using the formula x over n. All right, so that's how much information each question can provide to us, right? So we got 0.0787 divided by 0.0412. So we're looking at probability of z less than or equal to 1.91. And there you go, no more CDF. All right, so in this case, we want to be less than or equal, right? You look at the bell curve, this is z equal 1.91, and we want less than on the left-hand side of that. So we travel from negative infinities all the way until 1.91. So the command will be negative 10 to the 99, comma 1.91, comma 0, comma 1. All right, so about 0.972.
Just can you scroll up the page?
What is that, Victor?
Can you take the page up a little bit?
Oh, that's the end of the line, so I cannot
Oh.
scroll any further.
Okay.
Mhm.
Can see some of the numbers.
Can you see it better now, Victor?
Yeah, not really, but I'll figure it out.
Yeah, that's. Can you move the icons on your side around so you know the
Okay,
one
I'll do
from
it.
Zoom so you can see it?
Okay.
Is everyone have problem with the last page?
Can you scroll up a little bit so I can see the top of the page? Okay.
How about you, Victor? Can you see the whole thing now?
That's better. Thank you.
Okay. Okay, so again, everything is converting to z-scores, but you know you can recognize whether am I gonna use just a very simple z-score initially. Is if you look at chapter 7, you will not see anything about probability of the mean or probability of proportion. You don't see any of that, right? You just see one individual score, and notice that here they don't give you the sample, right? They said, okay, I have the means, I have standard deviation, I want to find out for one particular object or one particular person, right? If that person is selected, what is the probability that the person have IQ score more than 120 or less than 120, right? So right there. Chapter 8, you have a sample size, right? You have a sample size selected, and then you have the probability of the mean. Therefore, you're gonna use 8.1. So write out the formula. When you write your note, make sure you write a title, right? 8.1 talk about probability of the sample mean. Therefore, you say, oh, they talk about what is the chance of the sample mean, da, da, da. I know I have to use the formula in 8.1. And then you go to 8.2 when you write your note. So 8.2 talk about probability of sample proportion. Then when they talk about, okay, what is the chance that proportion gonna happen, percentage gonna happen, and so on, then you know that will be the formula I'm gonna use for 8.2. That's how you make the logic on your notes, okay? So don't just write the formula without notation or definition of the formula. Does that make sense, guys? Okay, so I'm just showing you how to write a good note for the exam so that when you do it, you don't have to go around just for the formula. And just for the record, for the note, it should be handwritten and not copy and paste, okay? And please don't share the note, right? Because the reason that I don't want to do copy and paste is that, you know, one person do the note and share to the rest of the group in Discord. That's not going to be helpful because when you write your own note, you know exactly where they are. Yes, but when you are sharing, use somebody notes, you don't know where they put the formula, so it will waste your time more than you write your own note. Make sense? Okay, so chapter 8, very short, only 2 sections. That be the main focus here. We're gonna use those 2 sections and make the modification for chapter 9. Okay, so let's take a lunch break right now, and when we come back, we will look at maybe one section of chapter 9. All right. Okay, so stop the sharing. All right, let's take 30 minutes lunch break. And if you are recording, you can pause your recording right now and resume after 30 minutes. However, we are using the sample to make the prediction for the populations, right? So chapter 9 focus on estimating the value of parameters. So if you go back to chapter 1, the difference between parameter and statistics is parameter is about population. Statistics is a summary of sample, right? So now we have all we need for the sample size And now we're gonna make that and use it for the prediction of the population. So 9.1, we estimating a population proportions, right? So in 8.1 and 8.2, right? So 8.1, we were talking about the sample mean, and 8.2, we talk about sample proportions. And chapter 9, we're gonna use that result in 9.8.2, and we make predictions for the whole population. So a few key points here is that we need to have a point of estimate. So the point of estimate for 8.1 will be x bar, and then for 8.2 was p hat, right? So p hat equal to x over n. We based on that, we can find out the point of estimate for the populations. And because we don't have the exact calculation for the population, so we do have uncertainty, right? So we have to have plus or minus of something, right? So we call that uncertainties, okay? All right, so let's get into that later. But now let's take a look at this example. A Pew Research Center poll of 1,007 randomly selected U.S. adults show that 856 of the respondents know what Twitter is. All right, so you can see here they are collecting around 1,007 random selected. So that will be the sample size, which is 1,007. So they show which return that 856 out of 1,007 know what Twitter is, right? So that's the probability of success that we have. So this one here is x, right? X equal to A56. Therefore, we can find the sample and then use that to find the population proportions, right? So p hat is equal to x over n, which is A56 divided by 1,007. All right, so this equal to 0.85. So roughly 85% out of 1,007 know exactly what Twitter is. So based on that, we can make a prediction for the US populations. Okay, so that's what we meant by using that. All right, so based on this survey, right, about 85% of US adults know what Twitter is. Okay, so because the sample is large enough and we have that, of course, we will have uncertainty for sure, right? You have plus and minus, plus minus. But now we said, well, this is the point of estimate, roughly around 85%. You know, if we do a survey for the entire population, it could be 86%, could be 84%, could be 87%, could be 83%, right? Depends on the uncertainty that we're going to have, okay? So this is what we call point of estimate. So we will not have the exact answer for the population. You know, when you think of the U.S. population, it's a lot, very big. So we always have some confidence where will this be, where will that be, and for that we focus on the uncertainty, and there will be a few level of uncertainties that we will have, right? So if you remember when you go back to the empirical rule, we have 68%, we have 95%, and we have 99.7%, right? So those are the uncertainty that we can fall within the certain area. So here we have what is called is confidence interval, or the interval of estimating, right? So we have the point of estimate, which is in the middle, and we say, okay, I can go less than that for a little bit, I can go more than that for a little bit, and how much more and how much less can I go is we call the confidence interval. And the point of estimate is always in the middle, and then we can have a lower level of confidence, and we can have a higher level of confidence, right? So you have a higher level of confidence, indicate that will be the longer confidence interval. And we have a lower level of confidence, indication that we will have a shorter confidence interval. So when you have 68% confident in comparison to 95% confident, then 95% will be much, much better than 68%, okay? And the vaccines that we have throughout our company, so they Pfizer, for example, they said roughly 95% fully vaccinated will not get the virus again, right? So that's how confident they are, 95%, right? So they look into that confidence interval that they have throughout 28,000 volunteer who took the vaccine. Okay, so that's a very solid evidence that they're providing. Okay, so we call that level of confidence. So we have a field, right? We have 90% confidence interval, we have 95% confident interval, and we have 99% confident interval. Therefore, in response to that, we have alpha to be 10%, alpha to be 5%, alpha to be 1%. So alpha is the percent that we are not confident. So if we are 90% confident, then we are 10% not confident. So alpha will be 10%. If we are 99% confident, then we are 1% not confident. Therefore, alpha will be 1%, which convert to 0.01 in decimal, if not for that case. All right. You can see here 95% level of confidence, mean that alpha is equal to 0.05, imply that if 100 different confidence intervals are constructed based on a different sample, we will expect 95 contain the parameters and 5 do not include the parameters, right? So that's the concept of that. All right. So confidence interval will equal to point estimate plus or minus the margin of error. When you driving on a freeway, even though the speed limit was 65%, but then sometimes you're driving 70% and, the police doesn't give you a ticket. However, if you go like 72, 75, they do pull you over and give you a ticket because they do have fine plus or minus uncertainty, right? You can go 5 miles more than 65 or 5 miles less than 65. It should be okay with that because that's the confident interval that we can play around with, right? As long as we're in that zone, we should be okay. Okay. All right. So chapter 9. Here we go. How do we construct the confidence interval for the population's proportion, right? So proportion will be the first thing we want to talk about here. All right. So in order to do that, the two conditions we need to satisfy will be n times p hat times 1 minus p hat must be more than 10, right? More than or equal to 10. And then the sample selecting have to be less than 5% of the population. So the second condition will almost fulfill every time. The only thing we need to check will be the first condition, which is n p hat 1 minus p hat bigger than or equal to 10, right? So that's all we want to make sure that's going to happen, right? So once we have that checking, then we can find the point of estimate, right? So the point of estimate again, p hat equal to x over n, right? So we can find the point of estimate. And then from there, we can find the margin of error, right? The uncertainty. So the margin of error will equal to z alpha over 2 times square root of p hat 1 minus p hat over n. All right, so now you see the appearance of z alpha over 2. Okay, so if you go back to chapter 7, the very last page of chapter 7, not this one right here, right? Z alpha. Remember that yesterday? Z alpha. So Z alpha tell us that we have to find the Z score such that the area to the right is alpha. Okay. So Z upon 1,5 equal to inverse norm 1 minus 0.15 comma 0 comma 1, right? Remember that from yesterday lessons, right? So that's how you find Z of alpha. So if you have Z of alpha will be inverse norm 1 minus alpha comma 0 comma 1, right? So for the TI 83, 84, but if you have the advanced ones, Z alpha will be inverse norm alpha 0 1 and then right. Okay, if you have the advanced one, you have TI 384, that's what you want to put. You have advanced one, you're going to select that option. Okay, so keep in mind that's how we define Z alpha in chapter 7. And here we go, we have Z alpha over 2. So we just divide the alpha by 2 and then we find the inverse for that. Okay. So once you found the margin of error and you have the point of estimate, you just minus E plus E to get the upper bound and the lower bound, and there we go. We all done, right? So that's the focus of that. All right. Any questions on the formulas and on Z of alpha over 2? All right. So remember, when you write your notes, make sure you write all that formula down, right? So as I mentioned before, it's all about find a number, plug into the formulas, and get the answer, right? Okay, so here is the example, right? A retirement confidence survey of 1153 worker, right? So there we go. So that's N equal to 1153. And retire in US 25 years of age or older. All right. So file that's 496. Yeah, for sure, Julia. All right. 496. So it's not percentage, so that's have to be my X. Had less than $10,000 in saving. Part A, obtain upon estimate for the populations. Right? So P hat equal to X over N, which is 496 divided by 1153. So this gives us 0.430. So the number of people who have less than 10,000 in saving is around 43%. Okay. All right, part B, verifying the requirement for constructing a confidence interval. Right. So we have N P hat 1 minus P hat must be bigger than or equal to 10. So we want to check that. And here just plug in a number. So 1153 times with 0.430, and then 1 minus 0.43, and you see whether it's bigger than 10 or not. All right, so this is 283, 82.6. So this is bigger than or equal to 10. right? And for sure, 1153 is less than or equal to 5% of capital N, right? So that's one for sure. So once that's done, we can go ahead and construct 95% confidence interval, right? So for that, we need to find E, and E depend on Z alpha over 2, right? All right, so we are 95% confident. Therefore, we are 5% not confident, which means alpha equal to 5%, or you convert to 0.05, okay? But we don't need alpha, we need alpha over 2, right? So that's the formula. We need alpha over 2, we don't need alpha. So we have to divide it by 2 before we find the Z of that, which indicate that alpha over 2 will be 0.025. And that's what we need to find Z. So Z alpha over 2 will equivalent to Z of 0.025. So I'm going to use the command for the regular calculator, not the advanced one. So you have the advanced one, you know what to do, okay? So I'm going to use inverse norm of 1 minus 0.025, comma 0, comma 1. All right, so this gives me 1.96. All right, you guys still with me on that? Yeah, we don't need alpha, we need alpha over 2. Yeah, Grayson. Which part are you still iffy about?
I'm a little confused as to I understand Z sub alpha over 2, but I don't understand how the stuff after that factors in the square root p hat 1 minus p hat over n. It seems like the Z sub alpha over 2 is already its own contained operation when you just plug in inverse norm. So having this extra thing after it's kind of confusing me because I'm not entirely too sure.
Yeah, so because we said, okay, this is your estimation, but how confident are you? Mean that we need to find the margin of error, right? So how much error are we going to make? And the error formula will contain, all right, first, let's see, when you see p hat 1 minus p hat over n, when you look at that in chapter 8, all right, so you see here, p 1 minus p divided by n, that's the standard deviation of p hat, yes? Okay. So in chapter 9, we said, okay, so let's see based on our standard deviation, and then we also look at the inverse Z, which is the area that we're gonna make for that we are not confident with, and see when you put those two multiply each other, we can be able to find the margin of error that we are going to not become confident with that.
So essentially this is Z sub A, or Z sub A over 2 times the standard deviation.
Of that proportion, yes.
Okay, I think I get it now.
Mm-hmm. Does that make sense?
It's beginning to.
Yeah, because, you know, if you go back to chapter 7, right? So how do we find the value of x? We find the value of x by taking, you know, mu plus with z times alpha. So
okay,
when you take x minus the mu, you are getting z times sigma, yes?
Okay.
And then that's how much of the gap that we're having. Does that
Okay.
make sense? Yeah, you want to say, okay, this is my point of estimate, and this is the actual value. So how much different they are? How much error are they making? And
Okay.
that come up with the value of E, which is Z times alpha.
That's
And then how do we find sigma? Sigma will be P1 over minus P over N, and that's how they put that together for the standard, the margin of error.
Okay.
Sounds good?
Yeah.
There we go. Okay. All right. So we have to find two independent things. We have to find Z alpha over 2, and then we have to find the sigma, which is that formulas right there. Okay. And feeling a bit better, Grayson?
Yeah.
All right.
think we're okay.
Sounds good. All
I have a
right.
question.
Yes, Matthew.
It's a silly one. On number C, I get everything, get the formulas. When you go inverse gnome, I have an advanced calculator, so it's 0.2501, then right, correct? Why is it right?
Because
Missing, I'm not finding that or seeing why we're doing that.
because right here, anytime Z alpha over 2, it will always focus on the area to the right of alpha.
Got it.
Uh-huh.
Okay.
Uh-huh. Remember percentile focus on the area to the left, yes?
Yeah.
And then
Told us
Z
that
alpha,
yesterday.
so Z alpha focus on the area to the right of alpha. That's
Okay.
the reason. And that's the reason why we have to do the right option for the calculators. All right, no worry. All right, everyone else, okay, before we moving on? All right, so now we have the Z alpha over 2. So keep in mind that you have to divide the alpha by 2 before you do the inverse, not inverse and then divide by 2. All right, don't do that. All right, so now E equal to Z alpha over 2 times with square root of P hat 1 minus P hat over N. And we just found it, so 1.96 times square root of 0.43, 1 minus 0.43, and divide by 1153, right? So the sample size is quite big. So that's, we can find the margin of error. So how much of the difference between the actual mean and the population mean, right? So that's what we try to find out.
I have a quick question. So when I did the inverse norm, how do I put that into the advanced calculator? Because I got the negative of that. I got negative 1.96.
Yeah, so when you want to have, you have the advanced one, just press second verse and then inverse norm, and you put just the area, so 0.025, and then you select right, and then you have to select the right options. Right.
I got it now. Okay.
That's how you're gonna get it. Okay. There you go. All right, so 1.96 times with 0.0129, so 30. All right. All right, so we get 0.02548. So after you have the margin of error, then you can find the lower bound and also the upper bound. So we have the lower bound will be P hat minus E. So we get 0.43 minus 0.02548. So 0.43 minus 0.02548. So we go from 0.0452, and the upper bound will be p hat plus e, which is 0.43 plus width 0.02548. So I'm looking at 0.4555. Okay. So what does that mean is that, all right, so here's the mean, right? Here's the proportion. So we're looking at 0.43. But then due to the uncertainty, we be okay if we found it's to be 0.405, or we can go up to 0.4555. So it's okay in that region, right? So we are about 95% okay. Okay, so so that's considered that as an accepted rate, right? If I have my result will be around 0.406, it'll be okay because it's within the region of 95%. Right, so the conclusions, all right, we are 95% confident that the population proportion is between okay, so that's how we explain that result that we just found. So we are 95% confident that the population proportion is between 0.405 and 0.455 within that region. It's acceptable.
And that's basically just saying we don't know exactly what the proportion is, but we suspect that it is between these numbers with 95% confidence. Okay, got it.
Mm-hmm. Mm-hmm. So now you can we can link that to the Pfizer vaccine. Yes, they said 95% effective, meaning that's okay. In that 28,000 sample that they collect, they will find how many people successfully have no side effect. Yes, and then based on that successfully side effect, they have this is my point of estimate, and then they calculate the uncertainty, and then they say, okay, we are 95% confident that it's 95% effective. That's how it works, and that's the information we got from the TV, and this is how we actually understood it, right? They don't know for sure, right? Because they only have 28,000 people. They don't have 2.9 billion people for the vaccine when they first started the experiment. Okay, so but they convinced us enough that it's 95% effective. All right, so please go ahead and give it a try for part D. So part D want us to find 99% confidence interval. Right, so part C we do together with 95%. Right, now your turns. All right, let's see you can get the 99% confident interval for the population proportion. Right, p hat still the same. The only thing different will be z alpha over 2. So that make a difference for those two.
Is p hat the same in D as it is in C?
Yes.
Okay.
All right. Are we good here, guys? All right. Okay, so when you see confidence interval proportion, just follow that step, right? Find out Z alpha over 2, find the inverse norm, and then find the E, and find low bound, upper bound. That's all you have to do, all right? Now, the second part of 9.1 is determine the sample size necessary for estimating population proportions within a specific margin of error, right? Now, when we start example 2, they select 1153. What's an odd number, right? Why not 1100? Why not 1200? Why not 2000? Why 1153? Well, so everything have a reason for that, right? So the next part is answering that question. So if we plan to collect sample data in order to estimate some population's proportion, how do we know how many sample units must be obtained? All right, so here is how the question got answered. If you know the p-hat, meaning that you watching the news or you read an article and I'm happens to present my research, and I said, well, based on my research, this is what I got for the p-hats. And you're like, okay, let's see if I can base on your p-hat and I want to do the exactly same research to see whether your one is better or my one is better. Then I need to know how many sample I need to select. And that is what's going on if you know p-hat, all right? So if you know p-hat in advance, right? So it's not your p-hat, somebody else research p-hat. Then to find the sample size required for you to do your own research, you must use the formula given as in the first box. So we need to have Z alpha over 2. We need to have P hat, and then we need to have E. All of that will be provided, right? Don't get me wrong. All of that will be provided. All you have to do is plug it in and get the answer. Now, the second case is you don't know P hat. So if you don't know P hat, then to get within a certain margin of error, you must use the second formula, which is Z alpha over 2 square times 0.25 divided by E square. So E square, so E will be in percentage, right? Okay, so E will be in percentage. Now look at Pfizer. The first time they doing a study to see how effective the vaccine is. This is the first time it's going to happen. Therefore, they cannot use the first formula. They have to use the second formula to see if they want to have a 95% successful, then how many participants they need to ask. That's what it is, okay? And that's the mentality that they want to achieve, and so on and so on. Does that make sense? Okay, so we have to depend on two situations. Do I know p hat in advance, or I don't know p hat in advance? And then we always route to the next integer no matter what. No matter what, right? For example, right, if n equal to 1122.1, we will use n equal to 1123, no matter what, okay? So why do we route up to the next integer? Because we doing an experiment, more will always better than less. Does that make sense? Right? So the more people we survey, the better result we're gonna have. So we always route up to the next integer. It doesn't follow, oh, if it's more than 5, we route it up. Now it doesn't follow that, right? We just have one thing, always route it up. So keep that in mind. All right, so here is example 3. An urban economics want to estimate the proportions of Americans who own their homes. What sample size would be obtained if he wished the estimate within 2 percentage points? There you go. That's the margin of error that he wants to have. Within 2 percentage points, we mean that plus or minus 2%. Okay, so from there, you know E will be 2% or 0.02. Okay. And then we have 90% confidence. So why do we need that? Well, we need that because we have to find Z, right? So that's the only reason we need 90% confidence. All right, part A. He used 2010 estimates of 0.669 obtained from the U.S. Census Bureau, right? So this guy here is P hat. So the instruction is very clear, right? You guys follow that, yeah? So they will give you everything, and then you just have to find it. It's not like, ooh, I don't know whether I'm gonna select the first one or second one. No, you have to know right away, right? So they give you that, right? Okay, so P hat is given and E is given. The only thing we need right now will be Z alpha over 2, right? So now we're gonna find Z alpha over 2. So 90% confidence mean that alpha equal to 10%, right? So when you are 90%, you are 10% not confident, which is 0.1. Therefore, alpha over 2 will be 0.1 over 2, which is 0.05. So Z alpha over 2 will be equivalent to Z of 0.05. And this gives us inverse norm 1 minus 0.05, comma 0, comma 1. And this one will be 1.645, right? So remember that I mentioned yesterday, right? For 90%, we will use 3 decimal for z-score, right? That's the reason I use 0.645. All right, so everything is done. I can find my sample size now. So since P hat is given, so I'm going to use the first one. All right, so we have n equal to z alpha over 2 square times with P hat 1 minus P hat divided by E squared. So 1.645 square times with 0.669, 1 minus 0.669, and divide that by 0.02 square. So the top one give me 0.5992 divided by 0.0004. There we go. So we get around 1498, right? So this is exact, so we're good to go, okay? So this one doesn't have decimal, so we will just use that 1498. So we need a sample size of 1498 in order to achieve what he wants to achieve. Make sense? And that's explained why example one, there's a 1153 workers, right? Because they want to have that at least what's the minimum they need to survey. That's what it is. Okay. All right. So now he does not use any prior estimate, right? So in this case, p hat is not given. So we're going to use the second formulas. Okay, everything the same except the p hat. So n is equal to z alpha over 2 square times with 0.25 and then divided by e squared. So we put it in 1.645 times with square that 0.25 and then divide by 0.02 squared. Okay. So we get 1691.5. So we will need a sample size of n equal to 1692. Okay. So we always route it to the next one if you see decimal. So when they don't know the result, then they have to use more than what they already have in the past, right? Which just makes sense, right? That's the idea here, okay? So again, this one just a minimum. So that's what we call that necessary, not just like you have to do exactly, right? You can do more, right? You can do 2,000 if you wanted to. You can do 2,500 if you wanted to. You can do 10,000 if you wanted to. But this is the bare minimum that you need to have in order to achieve what you want to achieve, okay? Does that make sense here, guys? Yeah. Okay, so normally exam cover chapter 7 to chapter 10 will be much easier than exam cover from chapter 1 to chapter 5, chapter 6, right? In my past 10 years, always the case, right? So I would say there's roughly 10% different. That's how much different first exam compared to second exams. All right, sounds good. And that's the end of 9.1. So we did, chapter 8 and the first part of chapter 9. That's okay. Tomorrow we finish the rest of chapter 9. And then what else? Oh, that's already Thursday tomorrow, right? So next week we do chapter 10. And then we will look at the exam review. And then before I give out the exam on Thursday, right? So remember, I do want you to have, independent weekends. Don't have to worry about the exam right after you come back. All right, so that should be it's for me today. We finish the chapter 9 tomorrow, and then next week we start chapter 10. Let me go ahead and take attendance before you guys log off, right? The homework should be available, right? Please go ahead and do those if you want. Right? All right, Ian, Abrika, and Grayson is here. Adam, all right, have a good day, Grayson. Adam,
I'm here.
thank you, Adam. And Matthew is here. Jackson,
Here.
thank you.